So let's say, for example, in a hospital, like you're collecting medical data, the data is very precious, it's very expensive to collect, and it takes a lot of time. So let's say, for example, this is, the time axis, okay? And you have one patient coming right there, okay? So this is the first patient. You take, collect medical data, maybe take a screenshot of the brain, basically brain scan them, take an MRI. Then this is the first time point, T0. Then this patient might be, let's say, labeled as normal, okay? So they might have symptoms of dementia, but they don't have dementia. Okay, it's just probably a weakness in the memory. Now, another time, maybe you wait for a few days. Okay, another patient comes, or maybe it's the same day, but you scan them, and it's they have some signs of having dementia. So you classify them as dementia. So this is the doctor doing this by sending the patient to do an MRI scan, and then getting the data, looking at the scan, writing a whole report, and then saying, well, doing this whole complex process. Now the problem is, if you want to train a machine learning and you are in a hospital facility and you're waiting for all these patients to come in, right? So you might have different labels and D. So at some point sometimes you might need to wait for a whole year to collect, it depends, let's say 100 samples, 100 MRI data. So a year is a long time, right? So let's say you waited for a year, you have this nice data, okay? Now you're gonna call this data my XTR. I'm gonna extract features from brain images. I have 100 samples, n equals to 100. I have the labels. I'm gonna train my model. Now if you want to test your model on unseen data, you might want, if you want to test it on 100 unseen data, what do you need to do in this case? Wait for one more year. Is that feasible? No, it's not feasible at all, right? So the machine learning basically community came up, or researchers, with a very brilliant concept. So let's say theoretically this is now let's say this is all the data you have, okay? So this is all my data. It lies in a very nice space or manifold, okay? So each data point, what is it? It's a long feature vector. Okay, remember, so it's represented by a long feature vector. Okay, so this is, this manifold belongs to R, D. So each point here has not only 3 coordinates. So 2 coordinates, it's a plane. 3 coordinates is a 3D space. A manifold can have even more, right? So it's a D-dimensional space. You're not in 3 plus 1 time. You're in 3 plus many other dimensions, because each point can have up to, I don't know, 500 features, 500 dimensions. Each feature is a dimension. This is very important. Now, how can we use, okay, all this new data, okay, let's say this is all I have, right? So this is all the data I have. How can I use this to train and test my model at the same time? So for those who have not been exposed to cross-validation, I want you guys to think about it, because this is not very obvious, right? So you have a set of data points, right? And you are allowed to use part of them to train your model. So your model can see what? For the training data, it's allowed to see the feature and the label, okay? The label that tells you N or D. Okay, so this is, each point has a feature vector and a label. But for the testing set, you should never use them and mix them with training set. So you should keep them separate, not touch them, leave them out, okay? So how can we do this? How can you train your model and test it using these samples? Let's say in your case, you only have collected N samples, equals maybe 1,000, so you have 1,000 samples. Let's be generous here. How can you use the 1,000 samples to train and test your data? So I want you to think about it and give me a few suggestions. Cross-validation. Kind of. Okay, so let's maybe just later on. Okay, so those who know nothing about cross-validation, I want you to go first, and then I'll give a chance to the other guys. Who doesn't know cross-validation? I know many of you don't. Okay, good. So, guys, what kind of idea you can come up with? So very simple. Go.
I have a question.
Yes.
Why do I have to use all the samples to test my, train my model?
You don't use, exactly, you don't need to use all the samples to train your model. Maybe half, yeah, so that's a good solution. So you can say, very good, you can say I will use 50% of my data for training my model and hide the 50% to test my model, right? Now, what is the problem with that? It's a good suggestion and people have used it before, but it does not allow you to check the generalizability of your model. So I'll explain it. So for example, let's say, hypothetically here, so you have, right, this is your data, right? So for example, I have something like that. So these are my samples right there. And I have, for example, a cross here, and then crosses right there. Okay? So let's say I somehow take as to train my model, I take those sets, okay, as training samples. So I'm going to train on those. So if I train on those, what does that mean? In this case, I'm going to remove them right here as if you're not seeing them at all. So what are your training samples in this case? These guys, right? So these guys are my training samples. So I want to draw a line that separates them. So the line would lie this way, probably to maximize the distance between the closest points, like these two guys, right? So I'm going to maybe put it this way, right? So now if you look, when I trained my model using this training data, okay, then when I tested it, it made one mistake, which is this guy, right? So the problem is, imagine if I change the training set, okay? So the training set, if I change it, so if I go back, okay, so if I change the training set, so let's say the training set in this example would be, right, so I'm gonna train, so let's select, for example, what I'm gonna hide, okay? So I'm gonna hide only those guys, okay? So this is my 50% maybe partition, or 40 to 60%. This is random, okay? I've done it once. Then what I'm gonna do, in this case, I need to classify. What I need to classify, I need to distinguish between triangles and dots. So this is my training data. So where I'm gonna put the line, so the line would be probably, well, it's quite problematic, but let's say to be, you know, if I want to really fit and maximize my accuracy, okay, so I would not, if I'm not allowed to make a lot of mistakes, I want to make less mistakes. So you can allow your model to relax them, you know, like its constrained. So here I say, I don't want to do mistakes, okay? I want my training accuracy to be very high. So I'm gonna draw the line right there, okay? So in this case, you can see that the line, the model that you learned is very different. If you remember, the other line was completely different, right? The direction, the model parameters, your W will be different. Now, what is the problem with that? Because the problem with that is you trained only on one training data that you randomly selected by randomly partitioning only one time, and then saying, okay, now I want to generalize my model, but you cannot really generalize because, you know, it's hard. You trained only once on a single data set. And also, you might have different cases. So you might, if you add new samples that you never saw before, they may lie on, you know, kind of this way, or maybe something like this, or maybe, you know, something a bit like that, okay? So you need to really come up with a more like smarter strategy rather than, you know, like just instead of only randomly partitioning and saying, oh, this is just training, this is just testing. So it is doable, but it's not the best evaluation strategy of your machine learning algorithm. So as an alternative option, what can we think of, like other ideas? where we can solve this problem. So I have somehow given you a hint. So here, what did I do in this demo? Right? So I give you like a small hint. Adding more, but before I added, I did two things. What did I do first and what did I do second? So I was using exactly the same points, but I did two different things. Changing the training samples, like changing what I'm hiding, right? So every time I say, right here, okay, I'm gonna choose some points as training set and then test on the hidden ones. And then in the next run, I'm gonna change my training set, train my model again, and then validate it on the hidden set. And I'm gonna do that many times, see how my model learns different parameters and what is the accuracy for all these runs. And then maybe I can take the average performance and say, now I can evaluate my model because I've seen how it learns given different data sets, okay? And how it generalizes it given different scenarios and distributions of testing set that was hidden. Let me explain that. So this is what we call cross-validation in a more theoretical way. So what is cross-validation? Cross-validation, so I'm gonna start with the simple case, which we call leave one out. Out cross-validation, okay? Cross-validation. So leave one out, it means leaving one sample out for testing, okay? So in this case, imagine we have these points. So this is all the data that I have. Okay? So what I do in the first run to train my model, I hide the first one out, okay? And I train my model on these data points using these images or these samples. So then I'm going to learn a first model W1, okay, for example. And then I will test it. So this is, during training, I will test it on the left out subject to predict its label. Okay, so this is, the left out subject, the testing sample, and I'm predicting its label. Now in the next run, what I'm going to do, I'm going to loop over all my subjects. So in the next run, I will leave this subject out, okay? And then select those subjects for training. I'm going to train another model, okay? And this model, it will give me the output for testing subject 2, okay? If I'm going to do this, testing subject 1, okay? So I'm going to loop over all of these guys one by one. Every time I'm leaving one subject out for testing and using the rest of the samples to train my model to maximize its training, because I want to expose it to a diverse sample so it can see many types of dogs and cats. That's why leave one out is generally one of the best strategies, because you're maximizing the number of your training samples and leaving one subject out. So if I run this, I loop over all samples, how many models I will train by the end of this one in the last run. So I'm going to hide this guy and train on all those guys, n-1, and I have 1. So how many times, if I loop over all data points, each time, n times, very good. So I'm going to train, I will be training here n models, and at the end, I will have a long feature vector, a long label vector, okay? And here it will have n values because every time I predicted for only one testing subject left out, okay? So this is my final predicted, label for label vector that I will compare with the ground truth label vector, because remember, for all these points, we also have the ground truth label vector, okay? So by comparing what you predicted, for example, 1 and here 1, so it's correct. But then here -1 and 1, so that's not correct. By comparing these two, you can get the accuracy, the classification accuracy. Now, there's another problem with this So you can see, guys, we're building solutions step by step. But there's another problem with this case. What is the problem? So we're leaving one subject out. Sometimes training an algorithm, machine learning algorithm, might take up to 4 hours, 3, 5, 6. It depends, right? It depends on the complexity, how many parameters it has, if you're using a GPU or not. So do you think if you have 1,000 samples and you just, designed a new machine learning algorithm, a classifier, and you want to test it, knowing that every time you train your classifier on n-1 samples, 999 samples, it will take 4 hours. So you're going to run it 4 times 1,000 samples using leave one out to evaluate it, to get the final predicted feature vector. Is that feasible? How many hours are you going to be waiting? It's not feasible, right? It's very painful. Now, there's another alternative, which is what we call, or maybe let's not call it. Can you think about an alternative? What is an alternative, right? So this is the best part of machine learning, when you do not know, or when you're learning about something and you're trying to think about how can I naturally find an intuitive solution to the problem. Okay? So think about it. What did we do here? It's very simple. Every time we had n samples, every time we use n-1 to train and leave only one out. It costs a lot of time. Now, I want to still evaluate my model, but I don't want to test it 1,000 times. I probably want to test it 5 times, or maybe less or more. How can I do that? Okay, so think about it. I'll give you 1 minute.
Can we test with pairs or
pairs?
Instead of one, leaving one.
Yeah, you leave 2 out.
3.
Yeah,
So
you're heading in the right direction. So you're leaving a bit more out.
So can we?
You know, or you don't know. You know, right? You're allowed to say, but I want those those who know, please, guys, keep it silent. Don't bust it up. Okay, so guys, I want you to think about it, right? Okay, 30 seconds. Think about it. So simple. If you give it to a kid, explain, might be intuitive. So, yeah, you're leaving 2 out, right?
So should we divide?
Yeah, maybe partition differently. Yeah.
So there are 2 different samples. So I will make a thread line onto this space.
Mm-hmm.
And between those 2 thread lines, I will take them as a training samples, because the out of those 2 training lines will be no matter. I mean, it wouldn't matter, because the problematic areas, I guess, between those 2.
Oh, you're talking about something way more advanced, but that's a very cool idea. We're gonna look at it, but yeah, so keep it at that right now. So you're saying basically, yeah, you're looking at where your models, where is the most ambiguous area, like most ambiguous samples, and then based on that, you're gonna define your training set and testing set, something like that. So you're heading in a good direction, but yeah, so that's not exactly the right solution, but you jumped far away to a more complex problem to solve on how to select training samples and how to select training samples. This is what we call sample selection. It's a whole research area in machine learning. Okay, good. So any other thoughts? Maybe more simpler? Okay, so I'll give you a solution. So maybe you can say, guys, what is the solution? Those who know? Okay, full. So give me the intuition. Don't tell me technically. What is the idea, basically? Any of you guys can go.
We can separate into k-folds like 20%.
No, tell me the basic idea, right? Like simple words, not 20%. Like just intuitively. Imagine that I'm a kid and I have a bunch of points, and then you want to explain that idea to me in a very simple way. Into why 2?
Or more.
Or more, yes. So partition into, you grouping your samples or partitioning the data into different groups, right? Into multiple groups. Now, once you group the data into multiple groups, what do you do with those groups? Now you can tell me, guys.
One group is training, the others. sorry, one is test, the others are all train, and then you could swap between, like you can choose a different group to test every time.
Right, so that's, yeah,
it's like
so
a
that's k-fold, what we
generalization
call k-fold cross-validation. And you can leave, you know, when you say 20%, so that's, you know, well, all you said is correct, but I wanted more like a laid-back, very simple explanation. So thank you, guys. So yeah, here, so basically what we're gonna do. So imagine we have, so this is the last part of the lecture. So now we're going into k-fold cross-validation, okay? K-fold CV, so it's not leave one out. So K is the number of the folds, or a fold is like a group, okay? It's like a group of points, your grouping points. So basically what you have, so imagine these are your points. Okay? So what I'm going to do, somehow I group them randomly together. So I partition the data randomly into 1, 2, 3, 4, 5 folds. Okay, so these are 5 folds. So now I'm going to generalize the concept. I'm going from particular case, leave one out, to general universal case, which is k-fold. So every time I'm leaving a whole fold out, I'm leaving these guys for testing, and I'm using all other folds for training. Okay? So, and in the next run, what I'm going to do, I'm going to leave this guy out for these guys out. Many guys now we have, like a whole fold out for testing, okay? And I'm going to use all these 4 remaining folds for training. How many times I'm going to train? How many models I will learn? How many learners I will train by doing this? 5 times, right? So yeah, so we have 5 models. Now, once you're testing, here in this case, what is the dimension of your label vector? 4, yes, because you are predicting for 4 testing samples at the same time. Okay, so this is very important. So the dimension of your matrix here also will be different, because you will have, in this case, maybe n prime samples. Okay, all the samples that exist in those remaining folds that you selected for training. So generally, in machine learning, there are 3 very common validation evaluation strategies, which are leave one out, cross-validation. We have 5-fold cross-validation, and we have 10-fold also cross-validation. So this is awesome, because I'm going to run my algorithm just 5 times, no matter what is the number I have for my data. This, I will run it just 10 times, training and testing, and this one n times, depending on the number of samples. So now you know what cross-validation is. So one important rule to not forget, very important rule, is, okay, is never mix training and testing samples. Okay? So even when you're normalizing data, we're going to see you always treat the testing set independently. You reproduce the same steps independently. You never access them when you're training your model. So this is very important.